afternoon, everyone. I am Chanda Devnath, one of the PMRF fellows. So, I am pursuing my PhD from IISER Berhampur. Right now, I'm a TA of this course. I am TA of this course, Mechanisms in Organic Chemistry. Here we will discuss usually some concept about this topic and also questions based on that. So let's start. Then this course is almost at the end. So till last week we discussed about trapping reaction intermediate to understand the reaction mechanism, where we talked about how to trap anion, cation, radical, and etc. And we also talked about the benzene intermediate and how we can trap that. After that we are discussing about different type of catalysis. So just moving on today's session, I gave one of the problem to solve by yourself. So let's try to solve that one. So here will be the solution, where they have given this alpha bromoketone and this methoxide base under methanol condition, and they got this one as their product. How this reaction takes place? In the last class we were discussing about this type of reaction. So it will be whenever there is a alpha bromoketone, if there is a alpha hydrogen adjacent to the ketone, that will get deprotonated and it will form this type of enolate will form. Then this enolate will come here, then bromine leaves from the system, and this comes here. From this type of cyclopropene ring, where the external nucleophile again comes and attacks to this carbonyl center, and it opens up, and after that when it come back, this ring get broke and you get our desired product. Okay, I think it's clear. So today's topic where we will discuss about different type of catalysis. So initially in the last week we started with we just started about acid and base catalysis and how the pH will affect the reaction where this reaction is acid catalysis, acid catalyzed, and where the reaction is base catalyzed. What we have seen that if a reaction is acid catalyzed, if the reaction is acid and acid catalyzed, then it will rate of the reaction will decrease with increase of pH, and if it is base catalyzed, rate of the reaction will increase with increase of pH. Now let's talk about something specifically. So if a reaction is specifically acid catalyzed, this is called specific acid catalysis, where the specific acid catalysis involve a rapid protonation of the compound followed by the slow step, which is accelerated in comparison with the uncatalyzed reaction because of the greater reactivity of the protonated compound. So what they are saying here, first our substrate will get protonated. In case of specific acid catalyst, our substrate will get protonated and form a cationic intermediate, and that will undergo further reaction and get our give our desired product. And in this case, this protonation step is the first step, and that after that the followed by step is the rate determining or the slow step. Rate determining or the slow step. Now if we see this example, here they have given this ester and they want to carry out the hydrolysis of the ester. Now if under specific catalyst condition, what will happen? This ester will get first protonated by simple H plus. It will get protonated. So this oxygen lone pair. Now you guys can have a confusion that there are two oxygen. Which will get protonated? Oxygen this one or this one? So the answer is this carbonyl oxygen. Why? This oxygen is sp2 hybridized, whereas this oxygen is sp3 hybridized. So between sp2 and sp3, which one is more electronegative? sp2, because of higher S character. Because of higher S character. So the molecule which is having a higher S character, that is more electronegative than that of the sp3 oxygen. Because of high electronegativity, suppose if it is a carbon or oxygen, which has more electronegative? Obviously oxygen, and that takes up the proton in a faster rate than that of the carbon. So whichever is more electronegative, that will take up the proton at a faster rate. That's why in case of this two oxygen, between these two oxygen, as this oxygen is sp2 hybridized, the sp2 hybridized oxygen will take up the proton at the faster rate. So this oxygen will take up this proton and get protonated, and after that water molecule will attack here and it will open up, and again there is a bond. So this comes here, and we get our desired product. So this is the specific acid catalyzed reaction. So this is the mechanism of specific acid catalyzed reaction. So in case of specific acid catalyzed reaction, first you have to protonate the substrate, and after that the reaction will follow up. So let's talk about an example. So they have given one allylic alcohol, and under acid catalysis this form a trans diene. This trans diene. So from the Hammett value, what we can see? The Hammett value is negative. Negative Hammett value denotes that it involves a positively charged intermediate. We have talked about the Hammett equation earlier. If anyone wants to know about that, you can go and check the previous uploaded videos, which is already in YouTube, and the links has been shared by the NPTEL also. So if the rho value is negative, it involves a positively charged intermediate. So there will be a generation of positively charged intermediate. And also from the Kh by Kd value, you can see that Kd is greater than Kh. Kd is greater than Kh, which means it shows a inverse kinetic isotope effect, which means it shows a inverse kinetic isotope effect. And whenever in a reaction there is an inverse kinetic isotope effect, that means that the hydrogen bond, the OH bond or the OD bond is not getting is not getting broken at the rate determining step. At the rate determining step. Okay, so from as if it is if the OD bond or the OH bond is broken at the rate determining step, we know that OD bond had greater bond strength, so the rate of the breaking OD bond will be slower. The rate of reaction having a OD bond will be slower because of greater bond strength. So from this, if we want to write the mechanism of this reaction, what will be the mechanism? So let's start. So whatever information we have got from these values, that the Hammett rho value is negative, it suggests that there is a positively charged carbocation intermediate. The second thing which we can know that the positive delta S value, that means the entropy change is positive delta S. That means after mean medium, positive delta S of the intermediate. This sign is for, this dagger sign is for intermediate. The del S dagger, this is called dagger. So del S dagger is positive. That means in case of generating the intermediate, the entropy will enhance. That means from a single molecule we will get a greater number of molecules because the entropy is increasing. We know about entropy. Whenever there is a enhancement of disorderness, that means there is a entropy enhancement. Suppose you are pouring a water from a glass, so what is happening? The water is getting spread on the floor, so the entropy of the water molecule is getting increases. So and the entropy enhancement of the entropy is always a spontaneous process. So enhancement of the entropy is always a spontaneous process. So from this one you can, so we've got another information that during formation of the intermediate there is an enhancement of the disorderness. So the positive entropy of activation suggests that at a rate determining step in which disorderness increases, perhaps one molecule breaks up into two. And the last information we got from this reaction, that there is the inverse solvent deuterium isotope effect, which strongly suggests there is the inverse kinetic isotope effect. So if you want to draw the mechanism based on this information, so what will happen? So there will be a generation of carbocation intermediate. So first, that means take up this proton and leave from the system. Generating this carbocation. So this will be first step. As this after that, the nucleophile So this will be our mechanism of our desired product. Understood? So this reaction is, so as the first step is the fast and the second step is the rate, the elimination step is the rate determining step. That's why this reaction, this elimination step is the rate determining step. That's why this is a specific acid catalyzed reaction. This is a specific acid catalyzed reaction. This is our solution of our problem. Okay, everyone can draw this one. I just give 5 seconds and then I will move to the next slide. Okay, let's move to our next slide. So they have asked for the mechanism, they have given a reaction here. This is another example of specific acid catalyzed reaction where this ketone undergoes a protonation, forming this type of protonated intermediate, and then this moves and one of the methyl gets shifted and form our desired phenol, substituted phenol compound. So from what is, if we notice what is the summary of specific acid catalyzed reaction. First one, this only H3O plus is the effective catalyst and pH alone matters in this reaction. Second is usually means rate determining reaction of the protonated substrate, because the protonation step is the first step and it actually means the reaction of the protonated substrate. The third one is the effective only at pH near or below pK of the substrate's conjugate base. Fourth, the proton transfer is not involved in the rate determining step. Only simple unimolecular or bimolecular steps. Therefore, a moderate or negative delta is value. Inverse solvent-ring citric isotopy effect is been seen. Okay, let's go to our next topic. Sorry, it will be specific base catalyst. Specific base catalysis. So specific base catalysis usually involves the removal of a proton from the substrate in a fast pre-equilibrium state Similar to the specific acid catalysis, the first step is the fast step. So here the first step is the pre-equilibrium deprotonation of the substrate step by um, step followed by a determining reaction of the anion, and most of the base catalysis reaction are usually uh, carried out by specific base catalysis. So a remarkable large inverse kinetic isotope effect is been seen in this type of catalysis. So you just remember, for specific acid and base both, you will see an inverse kinetic isotope effect. So if we see this example, there is a ammonium ion where it undergoes elimination type of reaction. As this group is highly electron withdrawing, so this hydrogen is highly acidic. This hydrogen is highly acidic because of strong electron withdrawing group. Because of strong electron withdrawing group. So therefore here there will be a deprotonation of this proton and forming this carbanion intermediate, and this intermediate, this anion comes here and remove the NR3 plus from the system. Here it will show a strong inverse kinetic isotope effect. So what is the summary of this reaction, this type of catalysis? Only OH minus is an effective catalyst, and pH only alone matters here. Similar to the specific acid catalysis reaction, usually means the rate determining reaction of the deprotonated species, and also effective only at pH near or above pK of the substrate. The proton transfer is not involved in the rate determining step, only a simple uni or bimolecular step, and a inverse kinetic isotope effect has been seen. Our next topic is general base catalysis. So even weak bases which are too weak to deprotonate a nucleophile by the mechanism we have just described in case of we have just described for in case of specific base catalyst where the proton gets deprotonated, where this proton gets deprotonated and forming this carbanion. But if the base is not that much strong to deprotonate at the substrate, what happens in this case? Also you can see catalysis by means of general base catalysis, where in this case the reaction depends not only on pH but also the concentration of the bases, because it's not getting deprotonated, it's just happening due to presence of those bases. In general, the base catalysis reaction, the proton transfer is not complete at the rate determining step but occurs during the rate determining step. In the previous one, what we are saying, that the abstraction of the proton is happening at the first step, and then after that the carbanion is taking place in reaction forming our product in the rate determining step. But in case of general base catalysis reaction, the deprotonation takes place at the rate determining step. The deprotonation step is the rate determining step. If we look into this example where this nucleophile is added to this electrophile and a catalyst, this base has been added, which give us our desired product, the acetylation of this alcohol, and this the catalyst get regenerated. If we see the mechanism, what we can see, that this general base will take up the proton from the alcohol, and this alcohol will attack to this electrophile. The general base will take up proton from the nucleophile, and this nucleophile will attack to the electrophile form at the rate determining state. After that, it undergoes a reaction forming our desired product. So in absence of, if that there is no such base is added, what will happen? In that case, the nucleophile is not getting charged or activated by our base. It itself attacks to the electrophile, forming the intermediate and give us our desired product. So in this case, what we can say, in absence of base also some reaction can take place. So that's why the role of base here just to activate the nucleophile to take place in a reaction. So its role is very minimal. So that's why it's called a general base catalyzed reaction, because it's not depend on the pH of the base, because the higher pH will not enhance the rate of the reaction, because it's not taking place in the reaction directly. It's just activating our nucleophile. It's just activating our nucleophile. So in the transition state, it's just taking the proton from the nucleophile, which is activating our nucleophile and stabilizing our transition state. Okay, understood? In case of specific base catalyzed reaction, in absence of base, no reaction will take place. In the absence of base, no reaction will take place, and the reaction highly depends on the pH of the reaction. The reaction highly depends on the pH of the reaction. But in case of general base catalysis reaction, the reaction can take place without base also, but in presence of base, the rate get enhanced due to activation of our nucleophile. So here two examples are given, where in one case a cyclopropane epoxide type of ring is formed, where in this case the desired product is THF. So why they are two different? Why they are two different? So here in this case, if we see that the first reaction which takes place, that first this proton deprotonate this OH, forming this O minus, and this O minus attack and get removed from the system and forming our desired product. Whereas in this case, the base just activates our nucleophile by taking up the proton, and no no anionic intermediate is formed, and it taking place in the reaction forming our desired product. So here the reaction is going from the mechanism, you can understand the reaction is going to a specific base catalyzed reaction, but in this case the reaction going through a general base catalyzed reaction. Why this discrimination? Because here you can see the product is highly strained. That's why our intermediate or the transition state is also a strained transition state. Therefore, the transition state is also have too much strain in itself. Because of that, it's very reluctant to take place in a reaction. Suppose the substrate, this is the energy level of the substrate, but as the transition state is highly strained, if the transition state, because of the huge bond strain, the transition state is not in high in energy, so it requires very high amount of energy to take place in a reaction. It requires a very high amount of energy to take place in the reaction. Whereas in this case, a 5-member ring is formed, which is not that much strain, or 5-member rings are stable. Because of that, the substrate is closer to the transition state, so it needs very less amount of energy to activate and take place in the reaction. Because of that, it can be activated by a very small amount of bases or the very weak base. That's why it shows a general base catalysis, but here we need a very strong basic condition. Because of that, it undergoes under condition of specific base catalysis. Okay, understood? I think whenever any reaction is not that much feasible under normal condition, that reaction needs a specific condition. That means that reaction is catalyzed by this specific condition. But if a reaction is feasible to form that product, then that it just need activation. In that case, a general catalysis can perform this reaction. Okay. So what is the summary of general base catalysis reaction? Any base is an effective catalyst and pH also matters. Proton transfer is involved in the rate determining step, effective at neutral pHs even if below pK of the substrate. Catalyst often much too weak a base to deprotonate the reagent. Catalyst removes the proton which is becoming more acidic in the rate determining step, and some other bond making or breaking also involved unless proton is on carbon. Often a termomolecular rate determining step is seen and it shows a normal kinetic isotope effect. So what is the difference from specific base catalysis reaction? That it will show a normal kinetic isotope effect because the proton is getting removed at the rate determining step. The substrate is getting deprotonated at the rate determining step. Our next topic which we will discuss about, that is general acid catalysis. In case of general acid catalysis, it involves the transfer of proton from a weak acid during the rate determining step. Similar to the general basic catalysis, here also the proton transfer takes place at the rate determining step, and similar to that, it will show a normal kinetic isotope effect because the proton transfer is taking place at the rate determining step. It will show a normal kinetic isotope effect. And there is also a very large negative delta. That means two molecules are combining to form one. So here one example is given. We have two. This is the ketone. So under acidic condition, it undergoes hydrolysis and form this ketone. So from this value of, here you can see that deuterated acetic acid has lower rate than that of the normal acetic acid. That means KH is greater than KD, which means it is a normal kinetic isotope effect. That means the proton is getting transferred at the rate determining step. So what will be the mechanism of this reaction? You can see that so what will happen here? This OET will take up a proton from this acetic acid at the rate determining step and forming this carbocation intermediate, and this carbocation intermediate is also stable because of this aromatic nature of this cyclic ring, and after that to hydrolysis it forms our desired product. Okay, just try to note down the mechanism. If this type of question came, then it will be easier for you to solve. So whenever there is a ketal hydrolysis type of reaction, and if there is a generation of stable cationic intermediate, it will go through a general acid catalyzed hydrolysis process. So the molecule have some features to stabilize the cation intermediate. The general acid catalyst can be found. So what is the summary of the general acid catalysis reaction? Any acid is effective catalyst. pH also matters, just opposite to that specific acid catalyzed reaction. Proton transfer is involved at the determining step. Catalyst will show a normal kinetic isotope effect. It will show a normal kinetic isotope effect. Okay. Let's move to our next slide, where if there is a general catalysis, like general acid catalysis and general basic catalysis. So in case of general acid catalysis, what will be the K observed with the concentration of the acid, and in case of general basic catalysis, what will be the rate of the reaction with the concentration of base. So in case of general catalysis, what we have said, that it also depends on the concentration. It also depends on the concentration of the bases or acid. So here, with increasing the concentration of the acid, what will happen? The rate of the reaction will enhance. Here also similarly, if increasing the concentration of the base, the rate of the reaction will increase. It's simple, right? In case of general acid or basic catalysis, the reaction is depend on the concentration of acid or base, because the deprotonation is taking place at the rate determining step. Due to that, it's directly involved in the reaction. That's why the rate of the reaction will enhance with the enhancing the concentration of the acid or base. So if we see if you want to check the change of rate with the pH, what you can see, in case of acid catalysis reaction, initially at low pH, the rate of the reaction is independent of pH. The rate of the reaction is independent of pH, but after the pK of the acid, after the point of pK of the acid, where the acid starts to dissociate, in that case, with enhancing the pH, what will happen? The dissociation of the acid will decrease because the pH is increasing. So that's why the reaction rate will decrease. Similarly, in case of basic catalysis reaction, what will happen? With enhancement of the pH, the dissociation of the base will increase. So that's why it will be dependent on the base catalyzed reaction. Now, after pK value, the pH, after pK value, the base will be all protonated by the water, and after that it will be independent of the base condition. It will be independent of the base concentration, because all base will be protonated by the water. Let's go to our next slide. So here we will just discuss about what is the difference between specific and general acid catalyzed reaction. So suppose a ketone is given and you have to perform this hydrolysis of the ketone. So suppose a ketone is given. So in case of specific base catalysis, what happens? It undergoes a protonation at the first step. That is taking place, and it undergoes a reaction at the rate determining step, forming our desired product. But in case of general acid catalysis reaction, the protonation takes place at the rate determining step, forming this intermediate, and after that to a fast step, it gives our desired product. A similar thing happens in case of general base catalyzed reaction. In case of general base catalyzed reaction, in case of specific base catalyzed reaction, the deprotonation of the substrate or the involvement of the nucleophile happens in the first step, forming this carbonic anionic intermediate. After that, through a slow rate determining step, it forms our desired product. But through general base catalyzed reaction, the base does not involve in the reaction directly, whereas it activates the nucleophile, and this nucleophile attacks to the substrate at the rate determining step, and after that, through proton transfer, it gives our desired product. Okay, so this is the simple thing. In case of specific acid or base catalyzed reaction, the acid or base directly involved in the first step, and that is not the rate determining step, whereas it followed by its rate determining step. But in case of general acid or base catalyzed reaction, there is no formation of carbocation or carbanion intermediate, whereas and the acid or base is not directly involved with the substrate, whereas the protonation of the substrate takes place at the rate determining step. In case of base catalyzed reaction also, the base directly doesn't attack to the substrate, whereas it activates the nucleophile to take place in a reaction with our given substrate. So here one reaction is given where you have to perform the hydrolysis of this ketone. This is partial hydrolysis taking place. So what will happen first? So initially in this case we have seen that this type of reaction is going through a general base catalysis reaction. This type of reaction is going through a general base catalysis reaction. So if it is general base catalysis reaction, general acid catalysis reaction, if this is a general acid catalysis reaction, what will happen? It will take up the proton. It will take up the proton from the acid at the determining step. Comes here, it gets removed from the system. After that, the water molecule will adapt to this carbon center. And through proton transfer, transfer, it gives our desired product. So proton transfer, it gives our desired product. So next, there are other different type of catalysis. We will just give a short overview of that. So next is Bronsted catalysis law. So in case of general acid or base catalysis, the acid or base react in the determining step. So rate of the reaction depends on the concentration of the acid and base that we have seen from the graph, and should there be dependence of the structure. So this is the general acid or base catalysis formula, where the rate of the reaction depends on the pKa of the acid and the base. The next type of catalysis we will discuss about, that is nucleophilic catalysis. In this case, we are adding a nucleophile to activate our substrate to take place in a reaction with our another the second substrate. Suppose one reaction is given. Suppose this reaction, we have to perform the hydrolysis of this anhydride. Just have to perform the hydrolysis of this anhydride and get our desired product acid. Now in this reaction, this part we have to remove from the system. Now it's a bad leaving group. It's a bad leaving group, and water is a weak nucleophile. Water is a weak nucleophile. So it has not that much power to involve a bad leaving group. So to remove a bad leaving group, we need a very strong nucleophile, or otherwise to remove to react a weak nucleophile. To remove any leaving group with a weak nucleophile, we have to make it a good leaving group. So what we can do, we can make this bad leaving group into a good leaving group. How can this possible? If we add in the reaction, if we add like 1 mole of pyridine, 1 mole of pyridine, what will do? This pyridine will attack to this carbonyl center and remove this acetate group from the system, forming this intermediate, where the leaving group is this positively charged pyridine. So this is a good leaving group. This is a good leaving group. In that case, the weak nucleophile water can easily remove this pyridine from the system and form our desired product, that is acid. Okay, so this is called nucleophilic catalysis, where we are adding an extra nucleophile to remove our bad leaving group and generating a substrate or an intermediate with a good leaving group, which can be easily removed by our second substrate or our given nucleophile. Okay, this is called nucleophilic catalysis. This is another example of this type of catalysis is esterification of acid. Why do we add? You can go and check that reaction, and we'll discuss this tomorrow. We'll discuss about this tomorrow. Tomorrow we'll discuss some question based on this total chapter. Whatever questions are there, we will just solve that one. Whatever questions come from this total entire chapter, whatever we have discussed in this last 8 weeks, based on that whatever question can be solved, we will just solve those questions. So this type of reaction, this is a homework for you. You guys go and check how this reaction takes place. Just go and check the mechanism of this reaction. Just go and check the mechanism of this reaction. Tomorrow I will discuss about it. So the next catalysis we will talk about, that is covalent catalysis. So catalysts form a covalent bond with a substrate, and after that when a catalyst form a covalent bond with a substrate and after that gets removed from the system and generating our desired product, that is called covalent catalysis. Next is enzyme catalysis. So this is the basic concept we get idea when we learn about catalysis. So we learn from the nature. Whatever we have learned, we try to mimic the nature. This is the first thing when people know about catalysis. The first thing which is the application of this is the enzyme catalysis in our biological system. So enzyme acts as a catalyst for any reaction in our body or any circumstances. In case of any biological species or in our nature, to happen any reaction in our body or any human body or any living beings, to accelerate the rate of the reaction, we need enzyme. So enzyme catalysis increase in the rate of the reaction process by an enzyme, a biological molecule. Most of the enzymes are protein, and most such processes are chemical reaction. Within the enzyme, generally catalysis occurs at a localized state and called the active state. So in case of enzyme, there is a active state, the specific state is there. So it react for a specific substrate. So see, it has this type of shape. So it will just react with a substrate having this type of shape, and it will go and fit into this shape and undergoes a catalysis, forming the product. After the product formation, this enzyme will remove this product from the system, and we get our desired product. So what is the role of this enzyme here? So enzyme is trapping our substrate, and it's helping to trapping our substrate and helping it to react, and after that when it becomes the product, it removes from the system, generating the enzyme back. What do you get in case of catalysis also? Catalysis comes in a reaction, take both the substrate in closer contact and reduce the energy of the activation state, and just after the formation of the product, it gets removed from the reaction and try to activate another molecule of the substrate, and these cycles goes on. Okay. And in case of specifically, it is not for another simple catalysis, but in case of enzyme catalysis, there is a specific active site where it can involve in a reaction, because if you want this enzyme want to react, it can't react from this place, it has to be from this place. So for enzyme, there is a specific criteria, it has a specific site that is called active site. So the another type of catalysis is phase transfer catalysis. This is one of the important catalysis right now, because the chemists and scientists trying to focus on the green chemistry, which is that we are trying to avoid the use of organic or the immiscible solvent which are harmful for the nature. So we are trying to perform a reaction in water medium in a greater extent. So suppose now a reaction is not a compound is not soluble in water. How can you take him into the water and make him react with our substrate? So it's possible if our reagent is, suppose our reagent is soluble in water but our substrate does not. So you have to take them both them closer into the same medium so that it will react. Otherwise both of them will be in the different phase. They will not come closer to react. In that case we need this catalyst, that is called phase transfer catalyst. In presence of this catalyst, the compound which is not soluble in another type of solvent, or the compound which is not soluble in aqueous phase or water phase, it make it soluble into the aqueous phase, or a part of it make it soluble to the in the aqueous phase, and let it react and give us our desired product. This is the one of the important type of catalysis in the modern chemistry, because in presence of this catalyst we can perform a reaction very easily irrespective of our substrate and product. Our substrate and reagent are miscible in the same solvent. So in a phase transfer catalyst is a catalyst that facilitates the transition state of a reactant from one phase into another phase where the reaction occurs. Phase transfer catalysis is a special form of catalysis and can act through a homogeneous or a heterogeneous catalysis method depending on the catalyst used. Ionic reactants are often soluble in aqueous phase but insoluble in organic phase, and in absence of phase transfer catalysis. Suppose a reagent, some salt is there, that will be soluble in aqueous phase, not in organic phase. The catalyst functions like a detergent or the solubilizing the salts into the organic phase. The phase transfer catalyst refers to the acceleration of the reaction upon the addition of the phase transfer catalyst. So here you can see in this diagram what is happening. In this diagram what is happening? In this case, the quaternary ammonium salt is soluble in water, whereas the NaCl is also soluble in water. But here in this case, when this RCl comes in contact by this interface, it reacts with the substrate and forming RCN and Q plus C, where there is a transfer from Cn to this R in presence of this quaternary, this phase transfer catalyst. This phase transfer catalyst helping him to react and forming this type of substrate where the NaCl is dissolved in water and RCl is soluble in aqueous solvent, but they react forming our desired product. Okay. So let's solve one of the question. So which crown ether is needed to achieve the following transformation? So crown ether is one of the important phase transfer catalyst where it's a cyclic ether. It can trap a cation depending on the size of the pore. If the crown ether core size is bigger, then it can trap a bigger cation like cesium. If the size is smaller, it can trap a smaller cation, that is sodium, potassium. So here they have given NaCN. So the cation is Na plus. there is a correct order. There is three types of crown ether. First one is twelve crown 4, that can 12 crown 4, 15 crown 5 and 18 crown 6. So 12 crown 4 usually can trap the lithium plus, 5 crown 5 can trap sodium plus, and 6 crown 18 is a bigger size, so it can trap the potassium plus. So therefore our desired substrate intermediate has this Na plus as a cation, so that's why we have to use this 15 crown 5 to trap this and react in the system. Okay, so thank you everyone. This much for today's class. Tomorrow there is an extra class. There we will discuss about different type of question based on this chapter. If you guys are interested, can come and attend tomorrow's class. And if you want if these classes are interesting to you, there are some previous classes which have been uploaded in YouTube. You can go and check those videos. I hope they can help. There we have discussed different type of questions, and tomorrow we will also discuss different type of questions, extra questions on this topic. Okay, thank you everyone. Have a nice day.